Okay. It's kind of weird. Got a white line sort of in the middle of my face on this. I'm not sure if it's showing up on your screen, but it's showing up on mine. Hey, my name is Mr. Dittmer. I'm an Algebra 2 teacher, and I'm teaching this lesson on verifying trigonometric identities. So the objective is to use trigonometric identities to simplify trigonometric expressions and to verify other identities. There it is. There it is. And write it down up there. Pause it, write it down. Good. So the deal with an identity is that it's always true. If we look at this, it's an equation that's always true. This is not an identity, right? You can solve it, x equals 3. But that means that this is only true when x equals 3. Only when x equals 3. That's an equation, not an identity. Not ID. An identity is true all the time. An identity is true all the time. For example, here's a couple of identities. The square root of x squared equals x. Those are the inverse things of each other, square rooting and squaring. So you always end up where you started. No matter what x is, this will be true. No matter what x is, this will be true. X plus 0 equals x. That's true for all x, right? X equals x. So these are identities. So we're going to talk about some identities that are true with trigonometry. And we're going to use identities to basically simplify some trigonometric expressions. And when I say simplify, we're going to try to basically turn them into, there's 6 trig identities. There's 6. There they are. And basically we can simplify them all into sine and cosine. We should really only have sine and cosine. And so the first one we're going to do is tangent. So just to figure out tangent, what I want you to realize is that sine and cosine, remember SOHCAHTOA. This is basically SOHCAHTOA right here. And then we're going to see, well, what happens when we divide sine divided by cosine? Well, if we have sine divided by cosine, that's opposite over hypotenuse divided by adjacent over hypotenuse. And that means that as a fraction can be rewritten as a division problem. A division problem can be rewritten as multiplying by the reciprocal. And when you do that multiplication, the h's cancel out and you have O over A, or tangent. So sine over cosine equals tangent. Tangent is sine over cosine. So that's one way you can use to sort of simplify these things. If you ever see sine over cosine, that's tangent. I forgot theta. So all these things, I could have written theta here. Theta. And especially, in all these, here, right? All right. Okay, so that's but that's an important identity, basically. You can, this proves it, but the identity is sine theta over cos theta equals tan theta. And theta is any angle. So it doesn't matter what theta is, 36 degrees, 360 degrees, negative 10 degrees. Sine theta over cos theta is tan theta. Got to know that. And it's true backwards, true. Tan theta is sine over the cos. Sine theta over cos theta. Theta is that Greek symbol. It means it's like a variable. Okay. The second important trig identity has to do with sine and cosine and what happens when how you bring them together. And so remember, we looked at the unit circle for a while, and we found out that at every one of these triangles, opposite is y. If the hypotenuse is 1, then opposite is y, and adjacent is x, because theta is down here. And so x is basically cosine, and y is basically sine, because opposite over 1 is just opposite, and adjacent over 1 is just adjacent. So you guys don't know what I'm talking about. All right. Let me refresh this. This is what I mean. In the unit circle, the cosine and sine functions of theta match up here because sine is opposite over hypotenuse. Hypotenuse is 1. So sine is opposite over 1. And therefore sine is opposite. So this is the sine. And the same thing with cosine and adjacent. Cosine is adjacent over hypotenuse, but hypotenuse is 1. So cosine is adjacent over 1, so cosine is the adjacent. So for every one of these points, the green is the cosine of theta, and the red is the sine of theta. So that's true. This is cosine theta, this is sine theta. And also, we know from the Pythagorean theorem that this squared plus this squared equals this squared. A squared plus b squared equals c squared. Well, if that's true, a squared, for this particular problem, a squared is 1/2 squared, and b squared is root 3 over 2 squared, and c squared is 1 squared. But since 1 squared is 1, the basic what we get is a squared plus b squared equals 1. And since that works anywhere I draw the triangle, no matter what theta is, it's still going to be cosine theta, sine theta. Therefore, the trig identity we have is cosine theta squared plus sine theta squared equals 1. This is always true for any angle theta. And we write it this way. We write it the red way. So when you're squaring the whole result, you just write it like this. But it means, blue is what it means, but red is how we write it. So this is the identity, cosine squared theta plus sine squared theta equals 1. And that's going to help us simplify some trig problems. Pause if you need to. So that's going to help us simplify cosine and sine. I told you we like to have things in cosine and sine because we can use this property to simplify sometimes. So other ways we can transform trig functions to cosine and sine. Tangent, I already told you about, is sine over cosine. Cotangent is the flip of tangent, so it's cosine over sine. Secant is the flip of cosine. Cosecant is the flip of sine. All right, and now I'm going to try to do a few examples using all these properties to solve some trig functions. So first one I'll do is on page 8. This is going to page 852, and I'll try number 9. It says simplify this expression. So this is number 9. It's secant. It says secant x plus 1 over times secant x minus 1 over tan x. So this looks big and complicated. The thing is, you got to start looking at whenever you see the secant of x or cosine of x or something like that. Well, you don't know what to do. Like, we don't know how to calculate it. But for the time being, we'll just treat it like we would treat an x. So we want to look at the top and just say, oh, just think of this as x plus 1 and think of this as x minus 1. And if we think of it that way, like that, then we're just FOILing. So it's x squared plus 1x minus 1x. So those cancel out, minus 1. So since that's what we're going with, we're doing the same thing. It's this squared, secant x squared. Now, since the whole thing is squared, secant x squared, we have this weird way of doing it. We put the little squared right there. So that means secant squared of x, and then minus 1. So that's our new simplification of the top. Okay, the bottom is tan x. Now, this is weird and odd, and I'm going to have to teach you a different part of the Pythagorean identity to explain how to do this. Too much, really. So we have secant squared x. So I'm going to use this identity. Now, how would I get secant into that? Well, secant is 1 divided by cosine, right? Secant and cosine are reciprocals. So if I divide both sides by cosine squared x, by the whole thing by cosine squared x, well, then I get this identity. I get dividing that, every single part of it, by cosine squared x. So divide, just put c for short, but we know we're dividing by cosine squared x. Cosine squared x, that's not a negative, that's just a mark. Cosine squared x over cosine squared x is 1. Sine squared x over cosine squared x, well, sine x over cos x, what's sine x over cos x? Oh, it's tangent. You guys see that? Sine over cosine is tangent, so sine squared x over cos squared x is tan squared x. And 1 over cosine squared x is secant squared x. So secant squared x is actually tan squared x plus 1. Why'd I bother to do that? Because that helps me do this. Secant squared x minus 1. Okay, what's secant squared x minus 1? Well, if I just subtract 1 from both sides, then I get secant squared x minus 1, and it's just tangent squared x is what's left. So, back over here, that's not what I meant to do. I know that secant squared x minus 1 equals tangent squared x over tangent x. And that also seems like, well, that seems a little weird. I don't know what to do with that, Mr. Dittmer. Well, it's kind of like, remember, you think of it as x. Think of this as, so this is just, if tan x is just x, then this is just x squared. And this is just x. So what's x squared over x? What's x squared over x? If you said it's x, you're correct. Therefore, tan squared x over tan x is just, pause it if you're not sure, it's just tan x. And that's that. So and now we really simplified, right? So we use those identities to change this mumbo jumbo into this. And the hard part was this thing where we found this out by messing with this. So this is another identity. You know, if you add to both sides an identity, you've still got an identity, and you can use that identity later on. Another identity that we could have done, we could have divided both sides by sine squared x, and then we'd have cotangent squared x, because cosine over sine is cotangent. So this is me taking the top and dividing by sine squared x plus 1 equals, and 1 over sine is cosecant squared x. So you can use that one too if you need to. But really they're all based on this one up here. This one. This is what we really need to know. This is the one that makes sense. All right, I can do one more thing. I feel like I gave you the difficult problem, and there was maybe some easier problems before it, and I think I need to go back in another video and do some easier problems. Let's see if I have time for one more. Number 10, number 13. Yeah. I think that's it. I'm gonna call this video over. Thanks for watching, and if there's another one, watch that one too. All right.